So where we left off last Thursday is we were looking at this example 1.5. It was the one where we made the histogram. I made a little bit of it with you by hand, and I used Minitab to make the rest of it. What were we looking at? We were looking at the percent of a state high school students are graduating on time, right? This table 1.1. The histogram I'm looking at is in figure 1.5 on page 23, and we talked about the shape of that histogram. I'd written down that it was single peak. In other words, I see one hump. You'll see people call this unimodal. That's all the same. Right? I see that one hump off to the right. And then you also tell me, remember I showed you three choices. You either got skewed to the left, skewed to the right, or roughly symmetric. And that one that we were looking at there turned out to be the tails going to the left. So you would tell me that was skewed left. Right, so there you're actually telling me what you see. You're interpreting the histogram for me. And I told you when you interpret, then you're describing the distribution. I have probably written down last Thursday when it's skewed to the left, got a tail going out to the left, as the value of your variable, right, as the percent of the state's population, the state high school students that graduate on time decreases, there are fewer and fewer states that have those lower and lower percentages. The majority of the states, now I'm still looking at the graph here, the majority of the states have between 75 and 90% of their high school seniors graduate on time. That's the chunk to the right. I got to write this part here one more time. You got a tail to the left. Right? Skew to the left, tail to the left. Skew to the right, tail to the right. That's where we finished on Thursday. Now, we got to talk about, anytime you're telling me about interpreting a histogram, describing a distribution, you always tell me about the shape. Tell me how many humps you see, skewed left, skewed right, roughly symmetric. Then you got to tell me about the center. And the center is supposed to be this 50-50 area point. Because if you're looking at that histogram, the bars, they're rectangles, right? They make up area. Okay? Now, that one being skewed to the left, you got to know that the center needs to be, it can't be in the middle of the picture there, right? It's not in the middle. It's got to be to the right. Now, I'm going to come over here, and I'm going to look here and see what the book tells me. And I'm on page 25 in that example 1.5. And it says, the center. Arranging the observations from table 1.1 in order of size shows that 80% is the midpoint of the distribution, the center. There are a total of 48 observations. If we cross off the 23 highest graduation rates and the 23 lowest graduation rates, we are left with two graduation rates, both of which are 80%. The center is their average. Now, I hate to break this to you. That's chapter 2. The guy just explained that shit to you. Now, I don't have, if I'm giving you something here, I'm not giving you the table to go along with it. Hell, I'm just handing you the histogram and asking you, where's the center? And I'm looking at this, and I'm hoping you're going to tell me the center is somewhere between 75 and 85. Right? Remember, I warned you about my multiple choice test. You're not going to have to pick between there. You know, I'm going to give you one in there, and then ones that are way off. Right? So, if I'm eyeballing this, the best I'm going to do is, I'm not going to give you a number off of this. You know, I'm saying somewhere between 75 and 85. If you tell me 77, I'm happy. You tell me 82%, I'm happy. All right? So I'm going to say between 75 to 85%. Remember, I'm just trying to chop it so somewhere there's half of the area to the left of this point and half of the area to the right, which means half the observations are smaller and half the observations are larger. I'm not worried about what the guy is saying in the example there. I just wanted to read that to you to warn you. When you read that, the dude's already in chapter 2. Okay? Now, when I think about the spread, okay, last Thursday I told you, give me the smallest and give me the largest. Well, I'm pretty sure the guy in the book's going to tell me exactly. He's going to tell me 59% to 88%. Well, I'm going to warn you again. Most of the time when I'm giving you things, you're just looking at the histogram. You don't have a table with the individuals and the value of the variable for each individual. What you got is a histogram. So when I look at that histogram and you ask me, what's the smallest possible? It looks like 55. What's the largest possible? 99. So it looks like 55% to 90%. Now, this is off your histogram. If you give me the table with all the data, no shit, I can read the smallest value, which is 59%, and I can read the largest value, which is 88. Yeah. Without the table, the best I can tell you is what's the smallest number you see in the histogram and what's the largest one. It's 55 to 90. You give me the table, you give me the data, yeah, I'll read the smallest and give you the largest, 59 and 88. Okay? Now, if I look at figure 1.5, the last thing we're supposed to talk about is, remember there's always 4 things you talk about with a histogram. Shape, center, spread, outliers. Do we see any extremes here? And I'm going to be honest with you. When I look on page 23 at figure 1.5, it looks like all of them just tucked up, or I don't see any outliers. Okay? What you're looking for is, here's your histogram, and you're looking for somebody stuck out this way, or you're looking for somebody stuck out that way, and I don't see that there. Now, the catch is, if I go to page 26, and I look at figure 1.6, this is still the same variable. This is still the same, the percent of high school, in each state, the percent of high school students that graduate on time. Except they changed the class widths. Instead of being of width 5, now they are of width, what is it? 3. They made the class width smaller. Now, question, is it still unimodal? Yeah, I know you see one big bar, but there's like one big hump over here, right? It's still unimodal. It's still single peaked. Is it still skewed to the left? Is there a tail out to the left? Yeah. Is the center still the same? Oh, shit, yeah, that's half-half, right? The center's still the same. Is the spread still the same? If you got the table, yeah. If I'm reading it off the chart here, I see 58 to 91. Okay, I'm reading the smallest and the largest value you see there. What changing the class widths did, you see how I got these ones out here to the left? Small n. Like there's somebody between 58 and 61, and it looks like there's 2 of them between 61 and 40. Well, it turns out those 3 states are, you've got 3 low individuals. Now, all semester, we're always interested, do we see outliers in the data? Okay? Because it screws up everything I want to do. Everything we want to do, outliers screw them up. So you want to check to see if you have any, because we're going to make some calculations in the next chapter. Well, there's 3 of them here, right? What are my 3? My 3 states that I notice here is D.C. That ain't even a state. That's at 58%, right? 59%? 58%? I got Nevada. And we have New Mexico. Nevada has a value of 62%. Look, if you're finding these, you're reading these off a table. I'm not looking at that histogram and telling you somebody's got 62%. And the other one's 63%. Now, here's the thing. Anytime you see individual observations stuck out in the tail, the first thing to check is, did somebody make an error writing things down? Did we make an error when we made the histogram? Well, I mean, the table is what it is. The histogram was made for us. We don't have any errors. So is there anything special about these? Is there any reason why D.C., Nevada, and New Mexico should have a lower percentage of high school graduates on time than the rest of the country? No, hell, they're just got smaller values. There's nothing special about them. Okay? So here's the thing. Are they outliers? Yeah, maybe. Are they out a little bit away from everybody else? Yeah, I can see it there when I change the class widths. Are they strong? Are they really far away from the rest of them? And the answer is no. Not strong outliers. Now, if you had a state that had 22% of their high school graduates graduating on time, that would be a strong one. That would be a long way away from the rest of them. But at 58, 62, 63, I understand there's a gap. These might be possible outliers. They're stuck a little bit out there, but they're not strong. They're not going to have a big influence on what we're wanting to do here. We didn't make a calculation error. We didn't write something down wrong. We didn't do a mistake when we made the histogram. I'm always looking to see if we screwed something up, is the deal here. All right? Now, at this point, students get a little concerned with me. And the reason is this. Is because if I give you figure 1.6, you might tell me you see outliers there. Well, I'm going to look at your histogram you give me, and if it looks like that and you tell me they're outliers, I'm going to say, yeah, that's what you see. If you give me figure 1.5 and you tell me, well, I don't see any outliers, well, yeah, I'm looking at that. Yeah, I don't see them. I'm going to actually look to see what the histogram is you made for me, right? And then if I give you a question on the test and I want you to tell me there's outliers in your histogram, oh, there won't be no doubt. Your histogram will be here. I'll have somebody stuck out here. Or your histogram will be here. I'll have somebody stuck out there. Right? Okay? The only thing that changing the class width does for us, it doesn't change the shape. It doesn't change the center. It doesn't really change the spread. It may help you spot some outliers or not. That's all. That's all that happened between these two. It's the same data. They changed the class width. You might have somebody stuck out the tail there a little bit. All right? To be honest with you, when you got an outlier that's really far away, strong one, I don't care what you make the class with, these are going to be far away. All right? Now, again, notice I've concentrated on the big picture. Yeah, I can see in figure 1.6, there's that one bar that's real tall and it comes down, and I'm still telling you you're seeing a single peak. Right? I just see this, one hump. All right? Now, I want to look at another one here that's in your book, and it's example 1.6, Iowa test scores. Figure 1.7, which is on page 27, displays the scores of all 947 7th grade students in the public schools in Gary, Indiana. Now, just to keep you remembering everything we've talked about up till now, you got 947 students. Yes, they're in Gary, Indiana. That's your individuals, right? There's 947 pieces of data there. And what did we measure on them? The vocabulary part is the score on the vocabulary part of the Iowa Test of Basic Skills. So it's a score, right? That's what it is. That's your variable. It's a test score. They just took the verbal part of, what was it? Iowa Test of Basic Skills. That's your variable, right? That's a quantitative variable. Now, I'm looking at this histogram, and there's a few things I want to point out to you. What would you tell me about the shape? Is that one roughly symmetric? Is that skewed to the left, or is that skewed to the right? Folks, in case you don't know, that's our most beautiful picture we see all semester of roughly symmetric, right? You fold it in the middle, left-hand side will lay on the right-hand side. Now, where's the center? When it's roughly symmetric, the center should be in the middle of the picture around what there? Notice it goes by halves, doesn't it? 2, 2.5, 3, 3.5, 4, 4, 4. I'm reading your classes. Yeah? It goes by halves. So if I was to pick something in the middle here, 6, 6.5, 7, would anybody be unhappy if I told you that the middle is around 7? Would you tell me 6.8? Would I be happy? Yeah. 7.2, around 7. Right? What's the spread here? What's the smallest possible score we see, and what's the largest possible score we see? The smallest possible is a 2, yes? I don't know if anybody has a 2, but reading that histogram, remember, we don't have the table this time, is 2, and what's the largest possible? 12.5, right? That's the largest possible, because remember, our class widths are a half. Do you see any possible outliers? There's something going on here between 12 and 12.5, but is it really that far away? No, right? The next one could be 11.5, and I got somebody at 12.1. So I might have possible outliers, but I don't see anything strong here at all. Okay? The only other warning here is read the y-axis. You know, look, when you're looking at a graph, remember the x-axis is your category, your quantitative variable here, right? It is the Iowa Test vocabulary score. What's the y-axis this time? It's not count. It's not how many fell in each class. It is the percent that fell in each class, yeah? So if I look at the class from 2 to 2.5, I mean, you're less than 1% in that group, right? If I look at the group from 6.5, 7 to 7.5, and I look up that bar there, I'm around 12%, yeah? It's a percentage. The bars are not representing a count, not how many. It's representing the percent that fell in that group out of the total of the 947. So that's a warning. The bars can be one of two things in a histogram. Either the count, how many, or a percent. What percent out of the total fell in that particular class? And then we got to do this last one. It's example 1.7. Just to show you that I'll have you brainwashed that there's only 3 shapes we ever look at. And eventually I'll have you brainwashed there's only one I really care about. Right? But there are other ones out there that don't fit one of the 3 we know. And it's example 1.7. Depending on where you went to high school, the answer to this question may be almost everybody or almost nobody. Figure 1.8 is a histogram of the percent of high school graduates in each state who took the SAT in 2013. Let me ask you guys. You guys are from the state of Tennessee, most of us, right? What test you take? Tennessee's an ACT state, right? So in Tennessee, would you expect to have a high percent take the SAT or a low percent? I would expect a low percent because most people are taking the ACT test, right? Okay? So when I look at that histogram, do not tell me you see something that is, look, don't tell me that's skewed to the right. You know what you actually see here? You see 2 separate groups. I'm going to do it like this in this example. I'm going to draw it for you real quick. No, I'm not going to write everything on there. I see this. And then I see this. I don't mean to make a gap there. You notice I didn't ask you for shape or anything. The thing that catches my eye here is this. You see that group there? Here's the problem with this. You had the same variable measured on every state, right? It's the percent of students taking the SAT test. The problem is you have 2 different types of states here, right? You got 2 groups going on here. You got SAT states and you have ACT states. Any idea which is the blue and which is the red? Which group is that? I'm going to label this. This is the percent taking the SAT. Anytime I see like 2 humps or 3 humps or 4 humps, what you've done is you've taken the variable and you've measured on this group of individuals, right? On this set of individuals. The problem is you have different groups inside of there. Like here, you measured this percent taking the SAT in a state for all 50 states. The problem is there's 2 groups. There's a categorical variable we're ignoring here, right? It's whether you're an ACT state or whether you're an SAT state. So what you've done is you've combined them all together. It does no good to interpret a histogram like that, where you're seeing more than 1 hump. I mean, that would be bimodal there, folks, right? 2 humps, double peaked. What is that trying to tell me? Oh, no. You have 2 groups of individuals in your data set. If I saw 3 humps, then there would be 3, right? Not necessarily for this, but if I saw 3 humps in the histogram, that's what I would be expecting to see. I have to stop and think. See, that doesn't look like it's skewed left, skewed right, or roughly symmetric. It looks like I got this chunk over here and I got that chunk over there. So you're not going to hear me describe center, spread, shape, outliers. If you want to do each one individually, we can, but not as a whole because there's these 2 groups there, right? There's the ACT states and the SAT states. Look, things aren't always perfect. Irregular shape. Two groups of individuals, all on the same histogram. I'm going to write bimodal, double peak. I see this, and it's trying to tell me that. If I had three, I'd be thinking about what variable I had measured and what three distinct groups am I looking at here that I have all in the same data set as my set of individuals. That's what I would think. That's what I'd be looking at. And I'd still tell you got an irregular shape. Now, I want to attack this from a different point of view. Look, I'm assuming I can draw any histogram up here I want, and you'll tell me whether it's skewed to the right, skewed to the left, roughly symmetric. Okay? So I'd like to go the other way. Okay? I would like to think about the shape roughly symmetric, skewed left, skewed right, and then I want to think about what variables can we measure that we would expect to see that shape in its histogram or its distribution. Okay? So when I think about roughly symmetric, right, remember that's where I always think about unimodal, right, single peaked, and I think about it falling, having this nice peak and then falling off both sides. If I think about heights, let's do it like this. It don't always have to be people. Lengths and weights of the same species. So if I look at the heights of women, and I had like 1,000 of them, and I measured their heights, and I made a histogram, I would expect to see something roughly symmetric. If I had their weights, and I made a histogram of their weights, I would expect that. If I did the same for men, either one, lengths, heights, weights, same. If I gave a perfect test, I would expect to see the grades on that test to be roughly symmetric. Okay? So what I'm asking you is what kind of things is, the majority of the observations are in the middle, and as we get larger, there's fewer and fewer, and as we get smaller, there's fewer and fewer. So I see that, those tails going out. Turns out that is, the perfect test would do that. SAT scores do that. ACT scores do that. Any kind of standardized test, hell, that's what they're shooting for, is something that's roughly symmetric in its distribution. What could I measure? Let's move to the next one. What kind of variable could I measure for something that was skewed to the left, where I have a tail going out to the left? The majority of the observations are on the high end. You already saw one, right? If I look at the states and I measure the percent of graduates, high school students that graduate on time, that was skewed to the left. What about if I gave a really easy test? What would you expect those scores to look like? Wouldn't you expect most of the people to do really well, and there'd be very few that did poorly? Easy test. What about if we pulled the coins out of our pocket and looked at the dates on them? Wouldn't you expect most of them to be new and there'd be very few old ones? Yeah? What about skewed to the right? What kind of thing? What can I measure here that would have a tail going out to the right and the majority would be on the smaller end of the scale? What about if I gave a really hard test? Wouldn't you expect most people to do poorly and there are very, very few that did really well, right? I was daydreaming, sorry. Okay. You always want to be able to go both ways. You know, if I give you the variable and then all of a sudden we make the histogram, you can tell me now. Where's the tail go? Is it roughly symmetric? Well, you need to think, we're thinking the other direction here, right? I got a shape in mind. What kind of variable could I measure that will have that distribution, right? So before I go to the next little part here, I want to go to your homework problems for just a second. I'm assuming that problem's still here. And it's one of the multiple choice questions. And I'm on page 37. Now, every now and then I'll go find us a multiple choice question that's at the end of your chapter there. I just want to have a little chat about it, especially after what I just did here. It says, you look at real estate ads for houses in Naples, Florida. There are many houses ranging from $200,000 to $500,000 in price. The few houses on the water, however, have prices up to $15 million. The distribution of house prices will be skewed to the left, roughly symmetric, skewed to the right. What are you expecting? The wording of the question is trying to tell you. You look at real estate ads for houses in Naples, Florida. There are many houses that range from $200,000 to $500,000, but the houses on the water, the few houses on the water, however, have prices up to $15 million. It's trying to tell you that's going to be, we expect those house prices in Naples, Florida to be skewed to the right. Do we expect house prices everywhere to be skewed to the right? You want to take the area here? All we're going to do is just pick the picture up and slide it down, right? What most houses here range from $50,000 to $250,000, and there's very few houses out here that are $1 million, $2 million, $3 million in our area, right? I still expect the house prices to be skewed to the right. What about what professional support you want to take? Let's look at their salaries. You want to take baseball? What's the salaries look like in baseball? It looks like most of the athletes probably make between $500,000 and $2 million. Aren't there very few that make $15 million, $20 million, $25 million? I'm expecting skewed to the right. Let's not pick just on baseball players. You want to do football players? Pick a professional sport, and it's going to be. I understand that where the big clump of them are will move depending on what sport you're thinking about, but there's still going to be very few making a whole lot of money, right? I would expect, okay, let's not pick on professional athletes. What about incomes in general? Don't I expect them to be skewed to the right? Yeah, in our area, look, I'm making shit up now. What's most people make between $20,000 and $150,000? There's very few people in our area that make $500,000, $750 million. That goes out and you get that tail, right? So I want to add these to this hard test. Incomes, I would expect to be skewed to the right. House prices, based off of that example in the book, and I just took it and turned it to pick anywhere in the country. You know, that range will be different, but you're still going to see on the high end there's fewer and fewer houses that have that price. Okay? Now, students always want to know, how do you turn the shit in class that you talk about into a multiple choice question? That's 1.22. That's a multiple choice question, right? That's how we turn it in there. Do we know what's going on? Okay? Now, there's one other type of graph for a quantitative variable. Remember, the most common one is a histogram, right? There's another one for a quantitative variable. Johnson City, how are we tonight?
All right.
We okay? It's called a stem plot. Now, there's an advantage of a stem plot over the histogram. Remember, the histogram will show you shape. You can eyeball the center. You can eyeball the spread. You can see if there's anybody stuck out in the tail's outliers. The problem with a histogram is you lose the individual pieces of data. Does everybody understand that? And that one we did before, I didn't know there was a 62 or a 63 or a 72. I don't know that. I just know how many is between these particular values. A stem plot, we don't lose the actual pieces of data. We can recover them. That's an advantage. The disadvantage is, if you're doing it by hand, you got to do a lot more work. Okay? Now, I understand on page 29, there's a little how-to. Right? Stem plot. To make a stem plot, we do this. I'm going to read the first part to you, and then 2 and 3, hell, I'm just going to do it. All right? It says, separate each observation, each piece of data, each value for each individual, separate it into 2 pieces. One is going to be into the stem, consisting of all but the rightmost digit, and then the leaf, which is the rightmost digit. So what you're going to do is, you're going to touch every piece of data, every value of the variable you're going to touch. You're going to divide it into a stem, and then the last digit there is your leaf. Okay? Then we'll go from there. What I would like to do is, example 1.8. They're going to change up here. They're going to give me a different set of data. They're going to change your variable. Table 1.2, which I'm guessing is on page 24. Page 24, there's a table 1.2. Presents the percents of state residents who were born outside the United States. In other words, here's what they did. They got the 50 states, and I'm assuming the District of Columbia is in there in table 1.2. There's 51 individuals in your data set, and what they measured was the percent of foreign-born residents in the 50 states and the District of Columbia. Okay? So I look here, Alabama has 3.4% of its population being foreign-born. New Mexico has 10.2. New York, 22.2. Texas, 16.5. California, 27.1. Florida, 19.4. Everybody got it? Okay. So if I want to make a stem plot, remember, you got 51, you got the 50 states, and you got D.C., right? This is this example 1.8. So we have to take every state, we have to take its percent, and we got to turn it into 2 pieces, a stem and a leaf. Now, warning, it has nothing to do with where the decimal place is. It just turns out that the data is given to us in terms of a percent, and it gives us the tenths position. It has nothing to do with, it's just this example works out like that. I still got to take the data, turn it into a stem and a leaf. So if you take, let's say, Alabama. AL stands for Alabama. I'm reading the table here. It's 3.4. What am I going to make the stem and what am I going to make the leaf? There is your stem. There is your, right? The rightmost digit's the leaf. Okay, let's take one like Arizona. Arizona is 13.4. There's my stem. There's my... You do that for all 50 states in the District of Columbia. Right? You just keep going. You'll make a stem, you'll make a leaf. The leaf is the rightmost digit. The stem is everything that's left over. Now, when you are done, you'll have all these stems, right? And the stems here, if I remember right, range from like 1 up to 27. In other words, there must be a state here which is 1.3. Which state is that? Oh, West Virginia, of course. It's all right. I'm from West Virginia. That's how I know it's got to be West Virginia, of course. West Virginia has 1.3. 1 would be the smallest stem because that's the smallest value, right? California has the largest. California has 27.1 of its population being foreign-born. So the smallest stem you see is 1, and the largest stem you will see is 27.1. Okay? So what you'll do is you will take the stems and you'll write them down. From the smallest to the largest, skipping none. I don't care if you got that stem or not, you skip none. 4, 5, 6. Yeah, I skipped some. I'd write 1 through 27 on my paper. Because I know the smallest value here is 1.3 and the largest is 27.1. So I know I got a stem of 1 and I got a stem of 27. Then what you do is you draw a line. So what you're getting ready to do is you're getting ready to separate the stems from the leaves. Then, for all the states that have a stem of 1, you put their leaves in increasing order out that particular stem. There's only one state that has a stem of 1, and it has a leaf of 3. Now, it turns out there are 5 states that have a stem of 2 when you are done. Somebody has a leaf of a 0, a 3, a 4, and a 9, 9. So I'm going to put those in increasing order. 0, 3, 4, 9, 9. And you continue all the way through. Every state is going to have a particular stem. It's going to have a leaf. All you make sure of is when you're looking at a stem, you put the leaves in increasing order going out that the leaves in increasing order going out that stem. And when you're done here, you would get a figure like figure 1.10 on page 30. How many little leaves are you expecting to see here? There's one for every state, right? I'm expecting 51 because I got the District of Columbia there. Okay? Now, before I didn't do very many of them. There was a reason. The same thing with the histogram. You're not going to make these by hand. Right? If the data set was small, yeah. 51 of them, I don't really think I want to do that by hand. Okay? Now, here's my thing. Just like a histogram has a shape, a center, a spread, and possible outliers, a stem plot has a shape, a center, spread, and possible outliers. And so when I'm looking, and I'm looking at this little stem plot in figure 110 right here. And as soon as somebody asks me, well, describe what you see, right? Interpret the stem plot, just like you would interpret a histogram. I can't interpret it like this, folks. What do? I turn the page 90 degrees. Now my little stems are on the bottom, right? And my leaves are coming up. Does that look like maybe some kind of histogram we'd be making? Yeah. That looks like a histogram. What's the shape here? If I got it turned like this. Anybody see a tail going out to the right? That's skewed to the right. The majority of the observations have values between what here? Between 2.0 and 6.7. I'm looking at that chunk that's to the right of the picture there, right? To the right of the stem plot. Do you notice as the value of the variable increases, in other words, as the percent of foreign residents in the state increases, there are fewer and fewer states, right? That's what the tail going to the right is telling you. Look, I warned you last week. I always give you 2. The stem plot's definitely skewed to the right. There's a tail going out to the right. Now, what the hell does that mean in this particular example? What does it mean in the context of this problem? Because I can draw anything that I want that's skewed to the right, and I want to know what it means in the context of this problem. It means the majority of the observations are on the low end of the scale here, right? Between 2 and 7%. And as the value of the variable increases, there are fewer and fewer states that have those high percentages. Now, what's the spread here? What's the smallest value you see in this stem plot? You ain't got to guess. You know it's 1.3. You can read that in the stem plot. What's the largest value you see? That's 27.1. You can recover that off of your stem plot. Do you see any possible outliers? Is there somebody, look, there's nobody stuck out to the left-hand side. Is there anybody stuck out to the right-hand side? What the hell is going on with California? Isn't that 27.1% of California's population is foreign-born? Is there anybody else stuck out there really far? There's somebody at 21.3 and 21.2. I'm just picking the 3 that are the farthest away, right? I'd really like to focus your eyes in on California, 27.1. Is that a mistake? Did somebody make a typo? Did we do it wrong? So what the hell is special about California? Remember what the variable is we're measuring here. It's the percent of the state's residents that are foreign-born. What does California border? Mexico. Are we shocked that California has such a high percentage of its residents being foreign-born? We're expecting that. You know what shocks me about this whole data set? What's the state next to California? Arizona. It's only got 13.4. What's the next one over? Look, I go there. That's how I know. The next one over is New Mexico. What's New Mexico? 10.2. What the hell's the next state over from New Mexico? I'm hoping it's like Texas. What's Texas? 16.5. What the hell's wrong with Arizona and New Mexico? You guys ever been to Arizona or New Mexico? Between Mexico and by the time you get through those states, there ain't shit there. It's desert. Of course, if I'm going from Mexico somewhere, I'm going to California or Texas. I'm not going to Arizona, New Mexico. Where's jobs at? Hell, they're in California and Texas. Have we made sense of why California appears to have a much larger value? Yeah, it's next to Mexico. There's jobs. Yeah. Okay? Now, one other thing I want to write on my little picture here is we did it by hand. You always need to keep track of, and I want to call it this. In other words, I'm asking you, when you have a number, there's place values, right? And what do? All the leaves here are in the tenths, yeah? So the leaf unit here is, I could write it as, the leaf unit belongs in the tenths position. Why do I need to know that? Can I recover the data now? You understand what the 1 and the 3 mean now, right? The 1's in the 1's position and the 3 is in the tenths position. So I know that I have a state that has 1.3, 2.0, 2.3, 2.4, 2.9, 2.9. I can recover the data. I didn't lose the data. That's the advantage of a stem plot over a histogram. You're not going to get anything else about shape, center, spread, or outliers. Hell, it's a picture. But what you retain here is you retain the values. Okay? Now, I want to come over here. I want to find that file. And notice in 1.8, the file, I got to find the file's title is foreign. Right? I'm looking right next to where it started on page 29. We'll find that file here. Exactly. Now, all this has done is it's put your table that's in the book, table, what was that, 1.2? They put it in a worksheet here at the bottom for us, right? There's my 50 states in the District of Columbia. Notice there's 51 total. There's the percent that are foreign-born for each one of them. I'm hoping it's the same ones that I just talked about, right? 3.4, 6.2, 13.4, 27.1. Yeah? I want to make a stem plot. Okay? So it's under graph. Same place as histogram, bar graph, pie chart. I come down here, and our book, Minitab calls it a stem and leaf. Right? Because there's stems and there's leaves there. So I choose the stem and leaf. It wants to know, what do you want to graph? I want to graph the percent of foreign-born, right? I put that in there. And then just to start with, I'm not going to screw with anything else on here. I'm just going to click OK and see what it gives me. Now, the difference between this and a histogram, it doesn't open in a new window. It gives me to me in the window up here. So Minitab's doing a couple of things for us. Ignore the left-hand column there all the way. You see the middle column? Those are your stems. It's done some crazy things, right? It's made the 0 there, 5 times, the 1's there 5 times, the 2's there 4 times. And then they've put the little leaves on them. Okay? Is that stem plot good enough for me? Yeah. Now, you see at the top where it says stem and leaf of percent foreign-born in? That's how many is in your individuals you have is 51. You see it says leaf unit is, they rounded things off before they started making, Minitab rounded things off before you started making the stem plot. So you notice on the 0 stem, which was the 1.3, right, that's what I get. You notice the 2 and the 7 down there? Well, that's 27, right? You've lost the 0.1. The 0, 1, that's West Virginia. You're just getting a 1 back. They round it off. The leaves are going in the 1's position in the place value of the number. Okay? Let's do one more. Stem plot. Stem and leaf. You see right here? Increment. I want to know, how do you want to step down your stems? Do you want the stems to go by 1s? Do you want them to go by 10s? Do you want them to go by hundreds? How did we do it when we did it by hand? They went 1, 2, 3. They went by 1s, right? That look like the one in the book? Right, now you know the stems are 1, 2, 3, 4, 5, 6, so on and so forth. That looks exactly like the one in the book. The leaf unit here is 0.1. It's telling you the leaves are going in the 10th position. I see 1.3, 2.0, 2.3, 2.4, 2.9, so on and so forth. Okay? Now, if you're wondering what's going on here all the way in the left-hand column, Minitab's trying to help your ass out. That's what they're trying to do here. He's trying to help you. And what he's doing is, he's trying to help you find the center. Does anybody see the 4 that has the parentheses around it? It's trying to tell you the center's on that stem. See, because it's counting both directions. You notice it's counting 1, 6, 12. And then it's counting the other direction, 1, 2, 5. It's counting both directions. And wherever the parentheses is, it's trying to tell you your center is on that particular stem. It's trying to tell you that. So if I was to look at that stem plot and tell you, okay, the center looks like it's 6.2. Well, hell, I'm just picking right in the middle of what's there, right? That's what it's doing. It's counting both directions. Wherever the parentheses is, oh no, the center's on there, right? Is it still skewed to the right? I don't know. I can't turn my monitor 90 degrees, so I got to turn my head that 90 degrees. It's skewed to the right. There's a tail going to the right. The center's around, well, it's in the 6th stem. So if you told me 6.1, 6.2, 6.2, or 6.7, I'm good. What's the spread? Smallest was 1.3. The largest was 27.1. Do we see any outliers? California, definitely a strong outlier at 27.1. And we had an explanation of California. Right? Look, I did that to make it look exactly like the book. That first one, I was happy. Just pay attention to what the leaf unit is so that you can see what's going on there. All right? That's all. Now, do you remember last Thursday when we made a histogram? I told you we could screw it up, right? You could get something that was a skyscraper or something that was a pancake. You can have the same problems with stem plots. That's when that little increment's going to play a role in what do you want to make. You want to bring things together or you want to spread things out. So here's what I'm going to do with a stem plot. And I'm going to call it problems. And the first one is, if I get a stem plot, actually my stem plot will look like this. Okay, I went through and I just took the data as it was, right? And I made the stems and I made the leaves, and it turns out I had 2 stems. Everything had a 12 or a 13, and then I had all these leaves. That's just the way the data looked, right? That's what the data looked like. So this is your little skyscraper, right? This is not good. We need to make more stems. And so the technique for handling this is called splitting stems. We're going to make twice as many stems. If you start with 2, you'll end up with 4. You start with 3, you'll end up with 6. So what you do is this. this technique is called splitting stems. Anytime you get everything and you're looking at a stem plot and all the little leaves are like on 2 stems or 3, that's not a good picture of the distribution, right? And so since I've got 2 here, 12 and 13, I'm going to write them down twice. Now, you see that first 12? You take all the leaves that are digits 0 through 4 and you put on that one. In other words, 0, 0, 2, 3. You see the second 12? You take all the leaves on that first 12 that are the digits 5 through 9. That first 13, you take all the leaves on the original 13 that are the digits 0 through 4. On the second 13, you take all the original leaves on the stem of 13 that are 5 through 9. Okay, so this was 0 through 4. That's 5 through 9. That one was also 0 through 4. The second one gets 5 through 9. Now, if you're back in Minitab and you see something like this, in Minitab you'll never see anything like this happening. I don't believe that it'll give you something screwed up where you got 2. It'll start splitting them for you. Remember that first one I showed you that had the 0s and the 1s and the 2s? It split the stems. It spread them out. Okay? Now, if we're doing it by hand, this is how you handle this. This technique is called splitting stems. You're doubling it. You're writing down the same stem twice. 0 through 4 and 5 through 9 on the second one. Now, what happens if we get this? This is the flip side of this. So, if you're looking at Minitab and you see something that looks like this, and you want to split the stems, you want to make the increments smaller. In other words, if the least units is 10s, you want to go to 1. Right? You want to make more stems. Okay? Now, what about if I've got data? I'm going to do it like this. Let's say I got 20 individuals. Okay? And I'm going to give you the largest and the smallest. The smallest value is 132. The largest value I see in my data set is, and then I'm going to give you one in the middle. Right? I just gave you 3. I gave you the largest, I gave you the smallest, and I gave you one in the middle. Okay? Remember, I got 20 individuals, so I got 20 pieces of data that fit between 132 and 967. What happens when I start making stems and leaves? Stem, leaf. Stem, leaf. Yeah? When I'm done, I know the smallest stem I'm going to see is 13, because remember that 132 is my smallest pieces of data. The largest stem I'm going to have is 96, because 967 was my largest pieces of data. So I'm going to have stems that range from what? I'm going to write stems down from 13 to 96. So I'm going to have what here? 84 stems? Give or take one? I got 84 stems and I got 20 pieces of data. This is the pancake. You got like 1 on 20 stems or whatever, and it's all spread out. Okay? My problem is I have too many stems. Now, you don't get to split them. You don't want to make more. You want to make less. So our technique for fixing this problem is, anybody remember how to we're going to round the data off. So when you round the data off, you'll have to take each one of them and you'll round them off. When you round 132, what's 132 become? 130. 453 becomes 450. 967 becomes right? 5 and above, you round up. 4 and down, you round down, right? Now, students usually hate when I do this next move. I don't need those zeros. Mark them off. Throw them away. Okay? Now what about when I start making stems and leaves? Stem, stem, stem. Leaf, leaf, leaf. How many stems am I going to have now? 10. 10 stems, 20 pieces of data. Things should be looking like a halfway decent picture here, right? So here I've got stems 1 through 9. Yeah? Better. Now, here's the catch. I make the stem plot just like I would have made it before. I'd write my stems down. I'd put my little leaves on there. Obviously, there's 17 pieces of data that I ignored that would fit in here somewhere. Yeah. How would I keep track of that I rounded stuff off and all of a sudden I chunked a 0 off? What's the leaf unit here? The leaf's actually sitting in the tens position, right? That's not 1.3. That's not 1.3. That's actually 130 that I recover, right? So when I go to, remember I told you the thing about the stem plot is you can recover the data. Well, you can recover the data up to if you had to round it off or not, okay? So I can recover 1. 3 is in the tens position, right? There's got to be a 0 there. I got the 4. The 5 is in the tens position. I'll never recover the exact data. I'll recover it up to the point where you rounded it off. That's how you handle it if you've got way too many stems in the data. And the leaf unit can be anywhere. It don't have to be the tens position. Hell, it can be the thousands position or the 10,000s position. It depends on what the numbers look like. I mean, think about it like this. If you're just taking baseball players' salaries and they make $1.3 million, you're going to deal with all them. You're going to deal with the 1.3 part, right? And the 3 is going to be in the, what is that, 100,000s position. Yeah? You just mark those zeros off then. They don't mean anything to us. And then I can recover the data. Look. A stem plot gives me the same information that a histogram does. You still talk about shape, center, spread, possible outliers. The nice thing about a stem plot is you still got the data staring you back in the face. That's all. Okay? Now, we're almost done with chapter 1. I'd like to come back here for 1 second. You know, I made this stem plot a couple times, right? Just to review last Thursday for a second. What's my other graph? My other type of graph is a histogram here, right? I wanted a histogram. Anybody got any feel for what you should be seeing here? Is there going to be a tail? And is the tail going to the left or is the tail going to the right? The tail's going to the right. The skewed to the right with the stem plot. You're going to be skewed to the right with the histogram. And then remember, the only other thing I ask you to do is I hate it when they mark stuff off in the middle of the bars. So I double-click the x-axis. I chose the binning, and I chose the cut point. That thing's skewed to the right, single-peaked. The majority of the states have between what? 0 and 9% of their population being foreign-born. Looks like there's a possible outlier here between 27 and 30. Hell, that must be California. Yeah? What's the spread here? The spread runs from 0 to 30 unless I have the table. If I got the table, it runs from 1.3 to 27.1. If I got the stem plot, it ran from 1.3 to 27.1. See, with the stem plot, we can be more precise because you have the data. Histogram, I don't know there's a 1.3. I don't know. I just know there's somebody between 27 and 30. Yeah? I got a possible outlier. My center's got to be somewhere around, what do you think? 6, 7 again, right? Because look, how many's here? I just wanted to show you this. There's 6 here, right? I mean, I know I can read it, but remember I showed you if I'm holding it over there, it'll tell me there's 6, 17, there's 23, right? Here there's another 8. That means there's 31 between 0 and 9. You see where I'm getting here? Remember, the one in the middle, if there's 51, then the one in the middle is going to have 25 and 25. Are they in order here? Is the x-axis in order? Look, I just read this to you back here that in example 1.5, that's how your author was telling you how to do shit. He was saying they're in order, put them in order. The hell, they're already in order. The center has to be between 6 and 9. Right? Because what I have, 6, 17 is 23, and then the next one took me to 31. The one that's sitting in the middle, there's 26th numbered one, right? It's got to be between 6 and 9. That makes sense to anybody. I'm just trying to get you to think about what we're looking at using the technology, because give me 10 minutes and I'm going to show you how to calculate the center. So if somebody's asking me here at this point, I'm just looking. I want to make sense of this. There's 6 here. I got 6 observations between 0 and 3. I got another 17 between 3 and 6. That means I have 23 between 0 and 6, right? 6 and 17 makes 23. They're in order. I'm reading from smallest to largest. The 26th one is the one that's in the middle here, right? You do understand if you have 51 things in order, the middle one is the 26th one. So I need to figure out where's the 26th one. Well, if there's 6, 17, and 8, there's 6, 23, 31. Shit, it must be in that third bar over there, right? That's the reason I said that the center's between 6 and 9. If I got the stem plot, well, it was on the stem that was a 6, and then I went right in the middle like at 6.2, right? Here, the best you're going to tell me is it's between 6 and 9%. Now, the last thing in this chapter is sometimes, not a lot of times in this class, we talk about something called a time plot. And what we have is, we have a variable measured over time. And I'm going to put it like this. When I say measured over time, your variable is usually measured over time periods. Like it might be measured every day or every week or every month or every 5 days or every year. But it's measured. You got some variable here that you're measuring over time, and it's set time intervals, set time periods. Right? What we are interested in is we're interested in change over time. We're interested in how the value of a variable changes as we go through time. I have 3 thoughts about this. Look, there's an example in your book here on page 33. It's called Water Levels in the Everglades. You can look at that when you go home. When I'm thinking about this change over time, if you was to make a time plot, down here is the time periods. Day, week, month, year, 5 years, whatever it is. You'll have it measured at different time periods, so that would be your little marks. You know, if you're measuring every year, it would be wherever they started to where they ended. Here is your variable. So you'll have different values of your variable. And so how you make a time plot is, at whatever time period, you have a value of the variable, right? So you come here and you make a little dot. Oh, that was the value at that time period. That was the value there. That was the value. That was the value. Right? So for every time period, you have a value of the variable that you can go up and you can go across and form the dot. And then you connect the dots with line segments. Draw the lines in. You do this. And, you know, there's going to be more time periods than that, but that's what you're seeing there. Right? You connect the dots with line segments. Then what we're interested in is, do we see any trends? Do we see any patterns in the time plot? I got 2 trends I'm interested in and maybe 1 pattern. You see this? If you look at a time plot and you see something, look, I'm just going to draw the time plot there. If I see this, and you come back and connect the dots, what's going on with the value of the variable over time? It's increasing. This is an upward trend. Lower left to upper right. The value of the variable increases over time. Anybody got a thought of a variable we could measure that if we made a time plot, in other words, we kept track of it every month for the last 10 years, that had increased over time? I got one here, pollution. You want to talk about the price of a loaf of bread? Yeah, those kind. Oh, no, the one you guys are all supposed to answer with. It's tuition. Tuition's increased over time, right? You would see lower left to upper right. Now, you notice like one time there I went down. No, I'm looking at the big picture. Did I start here, then did I end up? I mean, I can come down and go back up and down. It's just I'm looking for lower left to upper right. The value of the variable increases over time, whatever it is. And tuition was the one I had there. That's an upward trend. Another trend I would be looking for in a time plot is that's just the opposite, right? That's not an upward trend. You're reading the graph from left to right. That is a downward trend. What does that mean? That means the variable decreases over time. What variable can we measure that decreased over time? You got one? My friend's patience through the workday. We might measure that on a scale from 1 to 5, right? How about the, what's your favorite electronic device? The price of a computer has decreased over time. The price of the cell phone's decreased over time, right? Hopefully the number of deaths from cancer has decreased over time. Or pick another disease, right? That's a downward trend. And then the only other one that actually even makes sense for me to talk about is actually the one that's in the example. And what you see is this. Now, it's not perfect. Now, that's not an upward trend. That's not a downward trend. What's happening over time is the variable is repeating itself, right? It's cyclical. It repeats itself over time. It does this. Not an upward trend, not a downward trend. It repeats itself. Now, when you look at this example 1.9, it's cyclical. You see cycles. And what they're doing is, in case you want to know, they're measuring the water levels in one spot in the Everglades over time, and they measure it like, if I remember right, a couple, 3 or 4 times a year. And what happens to the water level? It does this. Well, from year to year, it repeats itself, right? It's cyclical. It's in cycles. Okay? Look, I didn't have a lot to say about time plots. They're in your book. I want you to know what's going on with them. If one shows up, you're looking for an upward trend, a downward trend, or cycles. If it's not that, then we're not really interested. Okay? You got some variable measured over time because we're interested in how it changes over time. Okay? Now, here's my last thought for this chapter. Okay? a time plot. Okay? When you think about a time plot, you think about something called time series data. Oh, I'm going to give you the translation because that's the statistics term. What you have is this. You have one individual. And you measure the variable over time periods. That's what you're seeing in a time plot. There's only one individual. And then what you're doing is you're measuring the same variable on that one individual at different time periods, right? Whether it's a long, up, down, cyclical. Yeah? What I want to do is I want to distinguish between time plot and a histogram. They're showing you different things. A time plot, there's only one individual in the data set. And you have that one variable measured on that one individual, and then you got that variable measured at different times. Okay? A histogram, just to get it in this language, not time series data, it's cross-sectional data. Translation. Many individuals measure the variable at one time. Now, you're not moving across time. You picked a time, you got a whole set of individuals, and you're going to measure the variable in that set of individuals. That would be like going to the Everglades and picking out 20 different places, and let's go all measure it on September 1st, 2015, measure all the water levels at all these 20 spots. That would be cross-sectional. One time, many individuals. Time series, time plot, one individual, many times. Histogram, many individuals, one time. Okay? That brings us to the end. Now, I'm thinking probably on Thursday. Look, we're not done for the night. I want to get started on the next one. On Thursday, I'll probably give you like a few problems to do for the next Tuesday. I'll pick them and then I'll write them up when I come in. If I want you to make a histogram or something, I'll tell you. Obviously, that's going to be done through Minitab, all right? But we'll do that on Thursday. Chapter 2, look, I know there's a chapter 1, and that was about graphs, right? Look, we got bar graphs, pie charts, categorical variables. Sim plots, histograms, that's quantitative, yep. Time plot, you measure the variable over time. Then we talked about shape, center, and spread and all that stuff. Chapter 2 is just a continuation. Yeah, they stop and give you some homework problems here, but to me it's a continuation because chapter 2, the title of it is Describing Distributions. Remember, distribution always tells you two things, what values and how often. Distributions with numbers. It's finally going to look like a math class. We're going to calculate something. And I'm going to be honest with you, we're going to calculate three things here. We're going to calculate center and spread. No more eyeballing for the center, saying, okay, where's the 50-50 area point? Where's half the observation smaller, half larger? We're going to calculate the center. No more just giving me the smallest and the largest for the spread, depending on whether you're looking at a table or a histogram or a stem plot. We're going to calculate, right? That's two things that, when we're done here, I hope that I've actually accomplished, that we can calculate the center and that we can calculate the spread, all right? And then the other thing I want to do is, see, the other thing I got to kind of be iffy with, and you guys haven't been around me long enough to know when I'm iffy, when I'm hand-waving. I hand waved at you today, and I hand waved some at you on last Thursday. Eyeball in the center, ooh, that's major hand waving on you. It's got to be here, right? The other thing I hand waved on you that I wasn't real firm on was talking about outliers. I just want you to know that they were out in the tails. So what I want is, we're going to calculate center and spread, and I want a formula to spot possible outliers. So, what do I got here? I got 1, 2, 3 calculations we're going to have. In other words, we're going to have a formula that says, depending on where you're at, whether you're a possible outlier or not. All right? So we'll give you a little calculation. That way I don't have to look at the histogram and say, well, yeah, there's a gap, but is the gap big enough? Okay? And then there's a graph here, but that's no problem. Now, here's where I'm at. I'm on page 47, and I've got some data here, and it says here are data, travel times for 15 North Carolina workers. So I've got 15 North Carolina workers. That's your individuals. That's your how many. What's the variable I have measured on them? It's travel time to work. And I'm just going to say travel time. Travel time is actually measured here in minutes, units. Okay? In case you don't know, I'm all the way back to chapter 1 on the who and the what. Travel time to work is a quantitative variable. That's the only time we calculate centers and spreads is when we're talking about a quantitative variable. Now, you notice I got a 30, a 20, a 10, 40, 25. 10. I'm just reading the data right there that's in the book. And they make a stem plot. Everybody see the stem plot? They got the stems 0 through 6, and then they put the leaves out there. My question is, how do they get a stem of 0? Does everybody see the person that only takes 5 minutes? That one? When you're trying to make a stem plot and you got a single digit, you got to do something here because you always have to have a stem and a leaf, right? Well, is anybody bothered by... You do realize those zeros are always in front of all our numbers. We just choose not to write them. Right? So I put the 0 there. And that will give me my stem and my leaf. The rest of them are okay because the 30 is going to be a 3 and a 0, the 20 is a 2 and a 0, 1 and a 0, and so on, right? The only one I wanted to point out to you is, look, you had somebody that had a single digit as their value, 5 minutes. How in the hell do I get a stem and a leaf? Put a 0 out front, the 0 is the stem, the 5 is the leaf. That's the stem plot. Now, when you look at that stem plot, all right, what's the shape? Is it, yeah, thank you for turning your head. Is it skewed to the right, skewed to the left, roughly symmetric? This has got a little skewed to the right, yeah? There's a little tail going out to the right. It's skewed right. Unimodal. Yeah? Now, what's the 2 things I'm supposed to ask next? Center and spread. What's this chapter about? Calculating center and spread. So I'm going to skip and say, do you see any outliers? Is there anybody that has like a much larger value than everybody? Well, there's somebody stuck a little bit out in the tail, right? At least there's like a blank stem there. There's somebody that takes 60 minutes where the next closest one is 40 minutes, right? So I'm going to do it like this. 60 minutes, that person is a possible outlier. Now, here's the thing. All right? You know, I always got 2 hands going for you. So when we come back on Thursday, there are 2 ways to measure the center. One you already know. Anybody know how to take the average of a set of numbers? Add them all up and divide by the total number? That's one of them. That's called your mean. That'll be the first one I show you. When you drive home tonight and you're going down the 4-lane, what the hell is that piece of grass in the middle called? That's your median. What's the median do? It divides these 2 lanes from those 2 lanes, right? One measure of the center is going to be the mean. You already know that one. The other one is going to be the median. Then we get the spread. There's 2 measures for the spread, right? So we're going to calculate come Thursday on mean, median, and then see what we can do about the spread, all right? Everybody be careful going to the house.